with arithmetic sequences where really like two sums were added together, something similar kind of works itself out here to get this special formula. Okay? So to find the formula, what we're going to actually do is multiply S sub n by r. Okay, so we have S sub n is equal to a plus ar squared plus ar cubed plus and so on, plus ar to the n minus 1. And what we're going to do is actually multiply that formula by r. So what that's going to do is give us r, S sub n, is equal to a times r is going to give me ar. Ar times r is going to give me ar squared. Ar squared is going to give me ar cubed. Ar cubed is going to give me ar to the fourth, and so on. Eventually I'll get ar to the n minus 1, and this will give me ar to the n, because really I'm going to have one more r in each of those terms. All right, so when I go to subtract these formulas from each other, which is what we're really going to want to do here to get them all to cancel out. Okay, when I subtract these, I get S sub n minus r S sub n is equal to a minus a r to the nth power. Then what I can do is factor out. So S sub n times 1 minus r is equal to a times 1 minus r to the nth. And then last but not least, I'll divide. So the sum is going to equal a times 1 minus r to the nth power over 1 minus r, and r just can't equal 1. Okay, well, think about it. If we're multiplying by 1, our sequence would just be the same number over and over and over again. So that's not really a geometric sequence anyway. All right, so that's really where this formula is coming from. So we want to find the sum of the first 5. What we're going to do is plug into that formula. So to get from 1 to 0.7, we're multiplying by 0.7. Easy peasy there. And we'll see it's the same. They tell us it's geometric, so we don't have to check anywhere else. So what we're going to do is that the sum is equal to the first term, a, which is 1, times 1 minus 0.7, which is r. Oops. To the n, we want, well, let's write it out first. To the n, we want the first 5 terms. So to the 5th term, or 5, over 1 minus r. Okay. And only r is getting raised to that 5th power, by the way. All right, so 1 times, that's going to give us 1 minus 0.7 to the 5th power, which is 0.16807. 1 minus 0.7 is going to give us 0.3. And then we just have a little bit more arithmetic to do here on top when I subtract, and then I'll divide. I'm going to get that's 2.7731, and that's our sum. All right, let's take a look at the next one. So this is really reading the same way. This is the sum, just in that special form. We could always go into our calculator, just like we had done, and work this out. But for this one, we are given that 5th partial sum. We know it's from 1 to 5, so that's how we know it's the 5th partial sum. Okay. So S sub 5 is really going to be equal to a. So our first term, if we plug in 1, r times negative 2 over 3 to the 1st power. So, I'm sorry, not r, 7. I don't know why I said r. So that's negative 14 over 3. That's my a. Okay. Then I have times that fraction. So it's 1 minus r to the 5th power over 1 minus r. So in order to figure out r, I just need one more of these. Or, honestly, I could use, I could just use this right here. This is my r. But if I wasn't sure, I could find another term. I could find another term and then find the ratio between them. So I have negative 2/3 here, negative 2/3 here. That is going to give us negative 14 over 3 times 1 plus 32 over 243 over 5/3. Yikes. And hopefully we'll let the calculator do a lot of this. We're going to get negative 770 over 243. A little bit messy there. Lastly, what is an infinite series? An expression of the form, the sum of a of k from k equals 1 to infinity, is called an infinite series. So that's really starting from 1 and going on forever, and this part is what makes it an infinite series. These dots here at the end just means it continues on and we are adding indefinitely. So let's consider this problem. You have a cake, and you want to eat it by first eating half the cake. Then you want to eat half of what remains, then again half of what remains, and continuing this process indefinitely, because at each stage some cake is going to remain. You can always have half of it, even if it's microscopic. We could be cutting all the way down. Now, does this mean we can't actually eat the entire cake? Well, of course not. I mean, logically, we know it's possible. But the idea is we can continually cut in half and half and half and half. Similar with radioactivity, similar with a few things that we looked at when we talked about exponential functions. We see how the circle is cut in half, and we can continue this process on and on. So here we have a half, and then that quarter is half of the half. There's then a quarter left over. And when we take half of that, it's an eighth. And then when we take half of the leftover 1/8, it's 1/16, and so on. So we can think of this as being this sequence, right? Or this sum, really. We're starting from k and we're going on forever, so k is 1. And really we have 1/2 to the k power, right? First time we have a half. The second time we have a quarter. The third time we have an eighth. We have a 16th. We have a 32nd, and so on. And we keep eating half and half and half, okay? So this is an infinite series, and we note two things about it. So first, it's clear that no matter how many terms are in the series, the total will never be greater than 1. Second, the more terms of the series, the closer we get to 1. So really what this is suggesting is that 1 can be thought of as saying a half plus a quarter plus an eighth plus a 16th plus a 32nd plus, and so on, 1/2 to the n, plus, and just keep going forever. So to then make this more precise, we can look at this in terms of partial sums. So we would say that the first partial sum is a half. The second partial sum is a half plus a quarter. The third partial sum is a half, a quarter, and an eighth. The fourth partial sum is a half, a quarter, an eighth, and a 16th. And when I actually add those together and get real answers here, this is a half. This is going to give us 3/4, 7/8, 15/16. And we're getting closer and closer and closer to that number 1. So we can say that if we take a look at these sums, this formula is going to give us 1 minus 1/2 to the nth power. So as n gets larger and larger, we're adding more and more of the terms in this series. So that would make n get larger as well. So if n's getting larger, then the sum has to be getting larger. And that's going to get closer and closer to what we consider to be the sum of the series. So notice that as n gets larger, 1/2 to the n gets closer and closer to being 0. So what really we can say is that as the series, as the sum becomes 1 or approaches 1, n goes off to infinity. So as the sum is approaching the number 1 or the value of 1, this happens as n is approaching infinity. So in general, if s of n gets closer or gets close to an infinite number, s, as n gets large, we say that the infinite series converges or is convergent. The number s is called the sum of the infinite series. And if an infinite series does not converge, we say that it is diverging or divergent. Okay. So an infinite series is a series of this form: AR plus AR plus AR squared plus AR cubed, and so on. Right? So we can apply this reasoning used to find the sum of an infinite geometric series. So the nth partial sum of a series such as this is given by the formula S sub n is equal to a times 1 minus r to the n over 1 minus r, where r cannot equal 1. Okay, and we knew that from before. It's shown that if the absolute value of r is less than 1, then r to the nth power gets close to 0 as n gets large. Okay. So if the absolute value of r is less than 1, then r to the n gets closer to 0 as n gets large. Okay. So what we can really say is that S of n is approaching a over 1 minus r as n approaches infinity. Okay. And really that's saying that as we're really basically subtracting nothing, we would get 1 in our numerator up here. Okay. All right, so that means that our sum here is going to be a over 1 minus r. So here we can define that for really any of our geometric series. Okay. We have this formula, and this is what we are going to use to get our sum each time. So if r is, the absolute value of r is less than 1, we're going to get this sum. If it is greater than or equal to 1, we say that it diverges, and we're not going to be able to get a sum. All right, so let's try an example. Let's determine whether the infinite geometric series is convergent or divergent. So the first thing we need to determine is what is r, and then is it less than 1, the absolute value of it, or is it greater than or equal to 1? All right, so let's find a and let's find r here. All right, so in order to find r, we need to see what am I multiplying by to get to the next number. So to get from 2 to 2/5, we're multiplying by 1 over 5. Same thing here, we're multiplying by 1 over 5, and so on. So that means that my r is going to equal 1/5. Well, the absolute value of 1/5 is certainly less than 1, so this is going to be convergent, or it converges. Convergence is the adjective. So now we want to find the sum. We're going to plug into that formula. So the sum is going to equal a, which is 2, over 1 minus 1/5. So that gives us 2 over, 4/5, and that's going to give us 5 over 2. Okay. All right, let's take a look at this next one. So again, how do I get from 1 to 7 over 5 to 7 over 5 squared and so on? It looks like we are multiplying by 7 over 5, so that's going to be what our r is. Okay. And if we take a look, is 7/5 the absolute value? Is that greater than or equal to 1, or is it going to be less than? And that is bigger than that 1, so we say that this is divergent. We want to find the